In this video, we are going to discuss how to find electric field at a point due to a spherical volume with non-uniform charge distribution. So in solve problem 2.4, you have a spherical volume of radius capital R that has a non-uniform charge distribution given as rho as a function of R equal to rho naught 1 minus small r over capital R for all values of small r less than equal to capital R, where capital R is the radius of the spherical volume and small r is any distance from the center, and it is equal to 0 for all values of small r greater than R. So basically the question is telling you that the charge distribution within the sphere is given by this function, whereas outside the sphere it is equal to 0, where rho naught is equal to 10 microcoulomb per meter cube and the radius of the sphere is 0.250 meter. We need to find what is the electric field produced by this charge distribution at R1 equals 0.125 meter, which is the distance within the sphere, and R2 equals 0.500 meter, which is the distance outside the sphere. So let us start with R1, a distance inside the sphere. So I take a point P at a distance R1, which is 0.125 meter from the center of the sphere. And we are going to find electric field at point P because of this charge distribution. We will be using Gauss's law. So let us construct a spherical Gaussian surface passing through point P, a distance R1 from the center. We know from Gauss's law the total flux through the Gaussian surface is numerically equal to the charge enclosed by the surface over epsilon naught. And we know from the definition of flux, I can write phi as integral E dot dA, and that is equal to the charge enclosed over epsilon naught. dA is the surface area for the Gaussian surface, and that for a sphere is given as 4 pi r squared. So we can rewrite the integral of E over the surface area to be equal to E times 4 pi r1 squared. R1 because that is the radius of my Gaussian surface, and this will be equal to charge enclosed over epsilon naught. We still need to find what is the charge enclosed within the Gaussian surface, and we will limit ourselves to the charge contained in this region. As by the definition of flux, we are only interested in the charge inside the Gaussian surface of radius r1 to find electric field at point P. So before we solve for the charge enclosed, let's rearrange this term to write in terms of Q. So we will rewrite this term as epsilon naught E 4 pi r1 squared equals charge enclosed, and I will call this equation 1. We will come back to this equation after we find the value of charge enclosed. We know that total charge Q for a spherical volume can be found by multiplying the volume charge density with the volume of the sphere. But here my volume charge density rho is not constant. It is varying as a function of distance r. So I can find the charge enclosed by integrating the charge density over the entire volume. We also know that volume of a sphere is given by V equals 4 pi 3 pi r cube. And when you take the derivative dV, you get this expression as 4 pi 3 pi. Derivative of r cube is 3 times r squared into dr. So we are using the substitution method of integration for dV here, and I can replace dV with 4 pi r squared dr. So let us solve for charge enclosed. We get Q enclosed equals integral rho dV, which is equal to integral rho times 4 pi r squared dr. And since we are integrating with respect to r here, we will take the limits from point 0 to r1. That means from the center of the sphere to a distance r1. Now let us substitute for rho. Rho for any points within the sphere is given as rho naught 1 minus small r over capital R times 4 pi r squared dr. Now we will take all the constant outside of the integral. Rho naught is a constant, 4 pi is a constant. So charge enclosed will be equal to rho naught 4 pi integral 0 to r1 multiply with r square in the bracket. So 1 times r square will give you r squared minus r times r square will give you r cube over r dr. Take integral of this term. We write rho naught 4 pi. Integral of r square is r cube by 3 minus integral of r cube will be r to the power 4 over 4 capital R. And this integration we are going to take from the limits of 0 to r1. Substitute the limits and you get the charge enclosed to be equal to rho naught 4 pi. We will replace r with r1. So r1 cube by 3 minus r1 to the power 4 over 4 capital R. So this is the charge enclosed within the Gaussian surface of radius r1. And we are going to substitute this value of charge enclosed in equation 1. So let's rewrite equation 1. Epsilon naught E 4 pi r1 squared equals charge enclosed. I'm going to substitute the charge enclosed here in this equation. So we get epsilon naught E 4 pi r1 squared equals rho naught 4 pi r1 cube by 3 minus r1 to the power 4 over 4 times capital R. We can cancel off the 4 pi from both sides and we can find E by dividing on both sides with epsilon naught r1 squared. So we get E equals rho naught over epsilon naught r1 squared r1 cube by 3 minus r1 to the power 4 4 times capital R. R1 is present in both terms inside the bracket. So I can take this inside the bracket to cancel off the common powers. Rho naught R naught over epsilon naught. Let's take R1 squared within the bracket. R1 cube over R1 squared times 3 minus R1 to the power 4 over R1 squared into 4R. Cancel off the R1s. R1 squared here and cube here, R1 squared here, and when you cancel this, this becomes R1 to the power 2. So we write for E to be equal to rho naught over epsilon naught R1 over 3 minus R1 squared over 4R. So this is the magnitude of electric field intensity at a distance R1 within the sphere. And I can substitute the values to solve for E as we know rho naught is equal to 10 microcoulomb per meter cube. So microcoulomb per meter cube I can write as 10 to the power negative 6 coulomb per meter cube. So rho naught will be 10 times 10 to the power negative 6 over epsilon naught is 8.85 times 10 to the power negative 12. Then you have R1 which is 0.125 over 3 minus 0.125 squared over 4 times R. R is 0.250. And when you solve this, you get the magnitude of electric field intensity to be equal to 29425.6 Newton per coulomb. Or you can write this as 2.94 times 10 to the power 4 Newton per coulomb. So this is my electric field at a point, a distance r1 within the sphere. Now let's discuss the second part of the question, where we need to find electric field at a distance r2 equals 0.500 meter, which is outside the sphere. So let this point be a distance r2 outside the sphere. Again, we will be constructing a spherical Gaussian surface passing through a point P, which is a distance r2 outside the sphere. And again, from Gauss's law, we can write total flux through the Gaussian surface will be equal to charge enclosed over epsilon naught. Total flux we write as integral E dot dA, which is equal to charge enclosed over epsilon naught. dA is the surface area of the Gaussian surface, and here the area of Gaussian surface is 4 pi r2 squared. So we write this integral E dot dA as E times 4 pi r2 squared, which is equal to charge enclosed over epsilon naught. Charge enclosed in the previous part of the question we found within the sphere to be equal to rho naught 4 pi r1 cube by 3 minus r1 to the power 4 over 4 times capital R, where this distance r1 was inside the sphere. To find total charge enclosed within the Gaussian surface of radius r2, I can just replace r1 here with the radius capital R of the sphere, because the total charge is only contained on the sphere. Outside the sphere, the charge distribution is equal to 0. So charge contained or charge enclosed within this Gaussian surface is equal to the total charge of the sphere. And we can write the total charge of the sphere by just replacing R1 here with capital R, the radius of the sphere. So we get charge enclosed equals rho naught 4 pi capital R1 cube by 3 minus R1 to the power 4 over 4R. Now let's substitute that here in our expression for E. I will write E equals charge enclosed over 4 pi R2 squared epsilon naught. Substitute for charge enclosed as rho naught 4 pi over 4 pi r2 squared epsilon naught r1 cube by 3 minus r1 to the power 4 over 4r. Now you can cancel the terms in the numerator and denominator. Here r to the power 4 will become r to the power 3. Cancel this r. And you get electric field to be equal to rho naught over r2 squared epsilon naught r1 cube by 3 minus r1 cube by 4. Now substitute the values. Rho naught is again 10 microcoulomb per meter cube, so 10 times 10 to the power negative 6. R2 is 0.500 squared. Epsilon naught is 8.85 times 10 to the power negative 12. Radius of the sphere is 0.250 cube by 3 minus 0.250 cube by 4. And when you solve this, you get electric field at a distance r2 from the center of the sphere to be equal to 5885.12 Newton per coulomb, or you can write this as 5.89 times 10 to the power 3 Newton per coulomb. So this is how you can find electric field at any point inside or outside a spherical volume with non-uniform charge density.